All right, so now we will begin a discussion on optics. Optics, of course, is basically the study of how light works. Light is a wave, and specifically it's an electromagnetic wave, which means it's composed of oscillating electric and magnetic fields. It propagates in a certain direction. In fact, it propagates in a direction that's always perpendicular to its electric and magnetic fields. But what you want to know is that it propagates with a velocity called c, which is the speed of light, 3 times 10 to the 8th meters per second. And at least it travels with this velocity specifically in vacuum. Vacuum, we'll also consider air to be like a vacuum. It's close enough. And so anytime you measure the velocity of light, it always moves with this specific speed, 3 times 10 to the 8th. No matter what, no matter if you're moving relative to the light, or the light itself, for instance, someone has a flashlight, they turn the flashlight on, you measure how fast it took for the light to get from the flashlight to your eyes, and you know the distance, so you can get the velocity is 3 times 10 to the 8th. Well, even if the person holding the flashlight is running towards you with a certain speed and then turns the light on, it doesn't make the light get to you faster. In fact, the light gets to you with the same speed. It's a very interesting effect that's discussed very prevalently in special relativity. But we're not going to worry so much about it now. This is just background information for you to understand. So the first thing we're going to want to discuss about light, at least the first big topic that will allow us to do some calculations, is called polarization. So as I said, light is a wave, and it's composed of an electric field and a magnetic field oscillating perpendicular to each other as the light propagates. So one way I'm going to attempt to show this is I've got the electric field, let's say, is oscillating up and down like this as the light moves to the right. So the electric field oscillates up and down. However, the magnetic field also oscillates, but instead of oscillating up and down, it's going to be perpendicular. So let's say it's front to back kind of a thing. Now, unfortunately, I'm not very good at drawing this too well, but hopefully you can kind of get a sense of this. So this blue wave is basically oscillating towards you and away from you, or kind of out of the screen and into the screen. And that's what the magnetic field does. So you have the electric field up and down, you have the magnetic field into and out of the screen, and all the while the wave itself is moving, actually propagating left to right. And that's exactly what a light wave is. So any light you see, and even those lights that you don't see, for instance, light itself, electromagnetic radiation, there's a whole spectrum of light. The light has certain characteristics. One big characteristic is how fast, for instance, does the wave oscillate? Does it oscillate very quickly or very slowly? That's called the frequency of the light. And so different frequencies basically give rise to different colors. So when you see light that's white or yellow or red or blue, that's all the same thing. It's all electromagnetic radiation. It's just how fast the light oscillates, how fast this wave oscillates up and down, determines what color you see. And in fact, if it oscillates very quickly or very slowly, it becomes invisible to you because your eye just can't pick it up. Your eye can only see certain frequencies. It has a very limited range. And those things that are out of the range of these frequencies, you just can't see. But they exist, and that's, of course, things like microwaves, what heats up the food in a microwave, or infrared, when you send, for instance, signals from a remote control to a cable box or something. A lot of times it's infrared. Radio waves, the information coming into your car antenna when you listen to the radio in your car. Those are light waves that oscillate at a very, a specific set of frequencies. We can't see it because our eyes can't see those frequency ranges, but it's light. Ultraviolet, so the light that comes from the sun that makes you sunburned, is not the light that you can actually see visibly, but it's actually an invisible frequency set of light in the ultraviolet range. And so that's why even if it's a very cloudy day, you can still be sunburned, because it turns out that ultraviolet light does not get blocked by clouds. It just goes right through clouds. And so, a lot of times you may think, oh, well, if it's cloudy outside, the light from the sun won't be hitting me so much, and so I won't get sunburned. But of course, that's not true, because the visible light is not what sunburns you. It's the ultraviolet. Anyway, all this is to say, one of the big characteristics of light is frequency, and that just means how fast, for instance, the electric field is oscillating up and down. If it does it very quickly, it's very high frequency. Very slowly, it's very low frequency. What does this have to do with polarization? Well, another characteristic of light is called polarization, and all it is defining the direction that the electric field oscillates. The way I drew it in this picture, the electric field is oscillating up and down. It's the black wave. But that was a choice. It didn't have to be up and down. It could have been at an angle. It could have been left and right. It could have been back and forth. There's a whole 360 degrees I can rotate this wave around the propagation axis, and it's still a light wave. There's no reason the electric field has to be up and down. And so the definition of the polarization of light is basically which direction does the electric field oscillate. So polarization is the direction of oscillation of the electric field. Now again, this is arbitrary because whoever defined polarization could have defined it as the direction of the magnetic field. That's perfectly fine too. But when it was defined as the direction for the electric field. So if we're looking at this example light wave I drew at the top, you would say the polarization is polarized, let's say, up. Of course, we mean up and down because it oscillates up and down, but we usually just choose one of the two directions, and so we say it's polarized up. If the electric field was oscillating, let's say, at an angle, then we would say the polarization is at some angle, call it theta, and we say theta is 30 degrees or whatever. Now, what's important about polarization? The thing is, you cannot see, your eyes at least, cannot detect polarization. When you see light, and if it's polarized up, or it's polarized left and right, doesn't matter. Your eyes can't tell the difference. So one would ask the question, well, if your eyes can't tell the difference, if you can't see any difference, then who cares what the polarization is? And it turns out it is important. Just because our eyes can't see the difference doesn't mean it doesn't actually have physical differences. And so it turns out Kodak invented a film which has the ability to block certain polarizations of light. For instance, if I have light, and the way I'm going to say this is I start with light polarized up. Okay, this is just a drawing, a way of specifying the polarization angle. I say it's polarized up, and I draw it like this. Now, if I send the light through this special film, if the film is made so that only light that's polarized left and right can get through, then what happens is no light gets through this film. So here's the original light. It's polarized 100% up and down, and I'm sending that light through this polarizing filter. So sometimes it's called a polarizing filter or just a polarizer. And so if I happen to send this specific up and down polarized light through a polarizing filter, which is set to only allow left and right polarized light, so that would be, we would say, the polarizer is polarized left and right. Okay, just a quicker way of saying it. So if we try to send this original light, which is polarized up, through a filter that's polarized to the right, none of the light can get through. And kind of a way of thinking about it is, if you look at this polarizing filter, you may want to imagine if it's polarized left and right, maybe there's a bunch of slits in this material. And so the only light that can get through has the light which is waving left and right like this. So if it waves horizontally, it can make it through. But if I try to send light that's polarized up and down, obviously up and down can't get through a hole that's horizontal. So these slits allow horizontally waving lights to get through, but if they're waving vertically, they can't get through. It's just the hole isn't big enough for it. Now, this isn't actually physically correct, but it helps our intuition. So, how is this helpful? Well, one way of considering, how polarization can be helpful is think about the sun. So the light from the sun, it comes out what's called unpolarized. Now, unpolarized is also called randomly polarized. And what it means is all the light that's coming out, some of the light is polarized up, some is polarized to the right, some's polarized at an angle. So it's just random. Every beam of light you get is polarized in a different direction. So overall, there's no total polarization. It's all random. Now, the way we reference that is we show the light polarization like this. That symbol says the light is unpolarized. It's just a way of notating it. So, light from the sun is unpolarized. It's coming in. If you have a polarizing filter that's polarized upwards, let's say, and you send this light through, this unpolarized light through it, then what happens is only those pieces of the original light that are polarized up will get through. So you get some light coming through. That light will now be polarized upwards because that's the only light that can get through. And all the other light that was polarized in the opposite direction gets blocked. And so it turns out you only keep 50% of the light. So of all the light coming from the sun, if you have a polarizing filter, then only half the light can get through, because the other half is, since this is random, is polarized in the opposite direction. So half the light gets blocked out, and then the light that doesn't get blocked, the light that goes through, you now know has to be polarized in the same direction as the polarizing filter. So if you think about it, sunglasses, the reason they have polarized sunglasses is for this exact thing. Polarizing sunglasses, or polarized sunglasses, they don't just have a tinted glass. They don't just make the glass itself dark. What it does is it has a certain polarizing filter built into it, and that polarizing filter blocks out half the sun's light. And so it's a perfect way of reducing the brightness without it just being trying to look through a dark piece of glass or something. Another good way this is helpful is there's a certain effect, I won't get into too much, but basically there's an effect which makes use of what's called Brewster's angle. Brewster's angle. And it goes like this. The sun's light comes in. Of course, it's unpolarized, so it's randomly polarized. If it comes in and reflects off some water or glass or a mirror or something, then the light that comes out as a reflection is polarized in a very specific way depending on the angle of incidence. And for a very, very special angle called Brewster's angle, if the light from the sun comes in at this angle, then all the light that comes out from the reflection is all polarized in a very single direction. And so if you have your sunglasses, which are polarized in the opposite direction from whatever this polarization reflection is going to be, then all of that reflected light will be blocked by your sunglasses. And so that's another big reason we have polarized sunglasses, because it turns out the angle of the light coming from the sun bouncing off of things like a pond or even like the back windshield of cars and things like this, that light is going to be polarized in a very specific direction every single time. And so they invent sunglasses to block all of that light out. And so it's a good way of getting rid of glare. Now, of course, there are other places polarization is important. For instance, one interesting thing is factories that make sugar syrups and things like this, sweeteners. In order for them to test how sweet their syrup is, the concentration of sugar in their syrup, they use polarization. Because it turns out when you send light, so if we have a little container, and this container has the sugar syrup in it, if you send light in, and let's say the light is polarized up, well, the sugar crystals in the syrup change the direction of the polarization. And so, if you know how much, how big your container is, you know how far the light goes through, then when the light comes out the other side, it'll be polarized in a different angle, a different direction. And the more sugar there is, the faster this angle changes. And so what companies will do is they'll send light that's polarized in a specific direction through a container of their syrup. They measure the polarization coming out, and they know if they want it to be a very specific percentage of sugar, a certain concentration, they know what this new angle should be for that concentration. And so they just affect the concentration until the polarization changes as much as they need it to. So polarization comes in a lot. Of course, one thing you could look up yourself, which is very interesting, is 3D glasses and 3D movies and TV and stuff like this. The way they do these 3D effects makes use of polarization. You have specific glasses. One lens is polarized in one direction, another lens is polarized in the other direction. And so the movie plays two different films at the same time. One of the films is the light coming from that film is polarized one way. The second film running at the same time over it, is polarized in the opposite direction. So each eye sees a different thing. Because, of course, let's say your right eye can only see up polarized light. So the movie that's polarized to the right gets blocked by that eye. But the other eye sees it because its polarization is the other. Anyway, these glasses, both the passive versions and the active versions, make use of polarization for you to be able to see these 3D effects. And it's a very interesting idea, so I would suggest you look into it when you have the time at just how do they use polarization to do the 3D movies. Now, what about a calculation? What kind of problems can we solve using polarization? Well, one thing we can do is we can ask the question, if I start with light polarized in a certain direction, and I place a series of polarizers in its way, in its path, and each one may be polarized in some different direction, the question is, how much light gets through the system of polarizers? Now, the way we're going to measure it is going to be by intensity, the intensity of the light, which is kind of like saying the brightness, the intensity of the light coming through a polarizing filter. There's a certain equation. It's called the law of malice. Now, it sounds like a nice evil law, but of course, it's spelled different. Malice, the evil version, is not the same as this law of malice. This is a guy's name, apparently. And the law of malice describes how the intensity of light changes as it goes through a polarizer. And it's a very easy law. What it says is the intensity of the light that goes through a polarizer is equal to the initial intensity, that is, how bright was your starting light, times the cosine squared of the angle for the polarizer. So as an example, let's take a simple example. Say we have light and it's polarized up. And the initial intensity, we'll call it I naught. I'm going to send this light through a filter. And this filter is polarized, and the way I'm going to do the notation is like this. So this notation means this filter is polarized 30 degrees with respect to the horizontal. Okay. And the question is, what is the intensity which makes it through the polarizer? How much light gets through, basically? And so we use the law of malice. It says, all right, the intensity that makes it through is, what did we start with? Well, we started with I naught. Of course, in a calculation, this might be a number, maybe 750 or 500 or something, whatever it is. The number we start with times cosine squared of an angle. Now, here's the important thing. This angle is the difference between where you start and where you try to go through. Okay, so that means you don't just take the angle that the polarizer is at. You got to say, what's my initial angle? Well, my initial angle for this problem, I'm polarized up. So with respect to the x-axis, this is 90 degrees. What am I trying to get through? I'm trying to get through a 30. So the angle is the difference between these two things. It's 90 minus 30. So I naught times the cosine squared of 60, which tells me 3/4 of I naught, or 0.75. So that's very important. Don't mistakenly say, the polarizer's at 30 degrees, so the angle in my cosine has to be 30. No. It's, what's my starting angle? In this case, it's 90. What am I trying to go through? I'm trying to get through a 30. So the angle is the difference between 90 minus 30. So what does this mean? Well, one thing it means is this. Let's say we start with light polarized upwards, and I try to pass it through a filter which is polarized horizontally. And we want to ask the same question, how much light gets through? Well, we say, okay, I equals I naught cosine squared of theta. So our initial intensity, let's just call it I naught cosine squared of theta. What's theta? Again, I'm starting at 90 degrees and I'm trying to get through 0 degrees. So it's cosine squared of 90 minus 0. So it's cosine squared of 90, and of course that is 0. That means no light can get through. But we already knew that. If we have up polarized light and we try to send it through a right polarizing filter, that light, because of the way the waves are oscillating up and down, can't get through the slits of this polarizing filter. So no light's going to get through. So the law of Malus works. Of course, it follows our intuition. But here's an interesting question. What would happen if I took exactly the same situation, but this time I put another polarizer in the way? And I put that polarizer at an angle of 30 degrees, let's say. So if we think about it, we say, okay, well, I start with light here. That light is completely blocked by this piece over here. So no matter what happens, this light cannot get through this filter. So it blocks everything. So if I just stick another filter in the way, and all the filters do is block, then you'd say, well, obviously you still are not going to get any light through. It's like you have light, you put a piece of paper in front of the light bulb, no light gets past the other side of the paper. If you stick another piece of paper in the way, you're still not going to get any light. However, if we go through the mathematics, we say, okay, well, how would we do this? It turns out the law of Malus is able to be used for a system of multiple polarizers. All you have to do is for each polarizer, you do another multiplying by a cosine squared. So, for instance, I start off I naught, then I have cosine squared of the first angle times cosine squared of the next angle. Because I have two polarizers, so I have two cosine squareds. So what are they? Well, the first one, notice, I'm starting at 90, and I'm trying to get through 30. So this first angle is going to be 60 degrees. Then the second one, the way to think about it, is now I'm starting at 30, and I'm trying to get through 0. So the next cosine squared is going to be 30 minus 0, which is 30. And if I do this calculation, obviously I'm not going to get 0 anymore. I get 3/4 from the first cosine squared, and I get 1/4 from the other one. So I get 3/16 I naught. Well, this is very weird. I start with a system, this one at the top, where I know this filter on the right blocks all the light completely. I take that system and I just put another block in the way. So you'd think, well, if I already blocked everything, I'm still going to block everything. I just put more stuff to help it block. However, when I do that, I don't block everything. I actually start to get light through. It completely violates our conceptual view of what's going on. And so what we have to do is realize that what happens when I get through a polarizer, the light is now polarized in the direction of that polarizer. So when I started with this up polarized light and I got through this 30-degree polarizer, the light that got through is now polarized in this direction. It's no longer polarized up and down anymore. The only amount of light that got through was that amount of light which is at this direction. Now that I'm at 30 degrees, there's no reason this 0-degree thing should completely block a 30-degree thing, because they're not perpendicular anymore. So some amount of this 30 degree can get through that 0, and now I have light that's now polarized horizontally. How much light do I have? 3/16 of what I started with. So it blocks a lot of it, but not all of it. So what do you take away from this? Well, first of all, if you have light that's polarized in one direction, and you immediately go to a polarizer that's polarized perpendicular, like this top example, you always block all the light. So light that tries to get through its perpendicular filter will always block everything. You'll always get 0. However, if there's something in between those two, so notice the light and this last filter are perpendicular, but there's something in between, all of a sudden that doesn't mean everything's blocked. You have to do the math. Now, even if you don't want to remember, if the light is perpendicular, you're going to block everything, all you got to do is do the math, follow the law of malice, and you'll get the right answer every single time. What's important is to remember the angle you use in the cosine is the difference in angles. I start at 90, I try to get through 30, so 90 minus 30 is 60. That's the first angle. Now I've gotten through. I'm now at 30. So I'm trying to get from 30 through 0, so 30 minus 0, that's my 30 here. Okay, so it's always the difference from where you are to where you're trying to go. The other thing you're going to want to watch out for is, what if I told you I start with unpolarized light? Well, if you start with unpolarized light, it would look like this. I'd say, okay, there's my unpolarized light. I'm now going to try to send this through a polarizer. Let's say the polarizer is up, and then I got another polarizer, and this guy is at 60 degrees. And I want to know how much light gets through this system. Well, the rule for unpolarized light, so this is unpolarized light here. The rule is, no matter what your first polarizer is, doesn't matter which direction it's angled at, you always get a half. So I'd say, okay, I is I naught, cosine squared, theta, this is my law of malice. So I'm going to say, okay, the first polarizer, here it is, and then the second polarizer is going to go here. The first polarizer, generally speaking, I would do cosine squared of theta. But because I started with unpolarized light, I don't have to do cosine squared theta. I just say 1/2 automatically. Now what happens when I do 1/2? This unpolarized light got through the first polarizer. I'm now polarized up because I got through an up polarized filter. Now I'm taking that up polarized light, trying to get through a 60. So I'm starting at 90. I'm trying to get through 60. So now I'm going to have a cosine squared of 90 minus 60, which is 30 degrees. Okay, so it's very similar to the second example, except since my original light was unpolarized to start with, the first cosine squared is not cosine squared, it's just a half. And that doesn't matter if this first polarizer is at an angle, let's say 30 degrees, I don't care what the angle is. If I start unpolarized, the first filter always gives me a half. Then you say you're now through that filter, and then you move on to the rest of the filters like you normally would. Cosine squared of 90 minus 60. If there's another one, cosine squared of whatever that one is. So that's very important for unpolarized light. You need to remember that. The first term is always a half. If you start with polarized light, then you start with cosine squareds from the very beginning. All right, so I hope this is helpful. I will see you next time with more optics.